Has this ever happened to you? Do you wish there was a way to make sure only you knew how to open your door? Well, boy, do I have the solution for you. It's time for you to learn all about combination locks. This video is going to answer a few key questions. 1. What the hell is a logic gate? 2. How do we use logic gates to achieve a desired set of outputs? 3. How do we simplify logical circuits in order to make them easier to build? And 4. How do we use this to actually make a combination lock? So let's dive into question 1. So I have here laid out in front of me 3 of the fundamental gates you need to know. We have the NOT gate, the OR gate, and the AND gate. And we're going to go from right to left, identifying what they do. So the NOT gate is the simplest of the 3. It's literally just a redstone torch on a block. As you can see, when X is 0 or not on, right? F1 is going to be 1 or on. So as you can see, turn it off. Whoa, it unpowers the torch, unpowers the lamp. That's crazy. Next up, we have the OR gate. So now the OR gate can have its output on when X or Y is turned on. So it's pretty easy to make. It's just repeaters going into blocks, and they share a redstone line going into your F1 output. We use repeaters because we don't do like this, because you can see there, now both those are on, and it kind of gets a little bit confusing. So we just use blocks like that. Now the AND gate is the most complicated, you could say, out of all of them. The AND gate consists of 3 redstone torches, 2 on the top and 1 on the side. As you can see here, these redstone torches are powering this dust, which is keeping this torch off. Now, if we power just one of these, power just X, right, you can see it doesn't really do anything. Your output is still off, nothing exciting is happening. But if we have both of them on, then our output is on. So an AND gate will only give an output when X and Y are 1 or on. Now the outputs of our gates can be illustrated using something called truth tables. So a truth table, right, is a table that shows all of the possible inputs that you can put into a logic gate and shows you all the possible outputs. So you can see here, for our NOT gate, there's only 2 available inputs, 0 and 1. And as you can see here, from what we saw in Minecraft, when it's 0, it's going to be 1, and when it's 1, it's going to be 0. And we can do the same thing for our OR gates. So you can see here, when both of them are 0, it's 0, but when one of them is 1, then it's 1, and when both of them are 1, it's also 1. So you can have X or Y be 1, and you'll output 1. And you can see here for the AND gate, it's the same thing that we saw again. Both X and Y have to be 1 in order for it to equal 1. Now, what you'll notice about these truth tables is that the inputs, they are counting up in binary. So you can see here 0, 0, 1, 1, 0, 1, 1. And now that we know what our logic gates do, it's time to put them into action. In order to make a circuit with the desired outputs we want, we first have to look at our truth table. As you can see here, we have an example truth table with 3 inputs, X, Y, and Z, and 1 output, F1. As you can see, F of 1 is true, or on, in 3 cases. 0, 0, 1, 0, 1, 0, and 0, 1, 1. We can express this using what's called a unsimplified logic equation. Now I know what you may be wondering. Whoa. What the fuck is a logic equation? Well, a logic equation is a way for us to express logic in a mathematical form. There are 3 basic functions of logic equations. There is AND, which is represented by multiplication, OR, which is represented by addition, and not, which is represented by a little tilde next to the input. Now, why do we assign addition to or and multiplication to and? Well, if you think about it, 1 plus 0 is still equal to 1. But 1 times 0 is going to be equal to 0. Anything times 0 is 0. So for an AND gate to be true, both of them have to be 1. 1 times 1 is equal to 1. So let's go ahead and apply that to our truth table. As you can see, we have 3 rows where f of 1 is true or equal to 1. So we have to write the sum of products that gets us to that output. So what does that mean? Well, if we take a look at our table, not x times not y times z plus not x times y times not z plus not x times y times z is equal to f1. We can see that each of these group of 3 terms correlates to a row in the truth table where f1 equals 1. As you can see, we have not x, where x is 0, not y, where y is 0, and z, where z is 1. That row gives us an output of 1. And we can do that for all of these, because any of these rows will output 1. So that means it's an OR function. So this is what's called a sum of products expression. So how do we translate this to actually building a circuit with logic gates? So here we have our unsimplified logic equation laid out in Minecraft. In order to identify the components, we have to color code it. So our output, F1, is yellow, our input Z is going to be purple, our input Y is going to be red, and our input X is going to be orange. All of our gates are represented by the same colors that they were earlier, with our AND gate being blue, our OR gate being green, and our NOT gate being pink. So if we go back to looking at the actual circuit itself, you can see that all of our inputs correspond to our equation. We have 3 not x inputs, we have a not y input and 2 regular y inputs, and 2 regular z inputs with 1 not z input. If we follow the lines, we can see that they line up with all of our products. As you can see here, we have not x times not y times z, leading to this 3 input AND gate. To make a 3 input AND gate, by the way, you just put 2 AND gates together. It's super easy. Anyways, for our second product, we have not x times y times not z. As you can see here, it goes into these two. And for our third product, we have not x times y times z. As you can see here. As you can see here, all the outputs of these AND gates are hooked up to a 3-input OR gate, which we make by, once again, hooking up 2 OR gates to each other. And this represents the addition in our unsimplified logic equation. So let's make sure our outputs correspond to our truth table. If we have not x, not y, and z on, our output turns on. If we have not x, y, and not z turned on, our output turns on. And finally, if we have not x, y, and z on, our output still stays on. But, I don't know if you noticed, this is a very big, very clunky contraption. So, how do we compact it? How do we make it easier to build this without having a million different redstone lines everywhere and taking up a huge space? So in order to simplify our circuit, we first need to simplify our logic expression. To do that, we do the same thing we would do in normal math, use algebra to simplify the equation. But when working with logic, we use a special type of algebra called Boolean algebra. Basically, this old guy, George Boole, was like, hey, what if we did algebra, but the variables could only be 1 or 0, also known as true or false, instead of the traditional number system we see in normal algebra, where variables can be any number from negative infinity to positive infinity. So, how do we go about simplifying this equation? Well, all 3 of our products have a common factor of not x, so we can pull out our not x to the front, and we get not x times the sum of not yz plus y not z plus yz. So our next step is going to be finding a way to combine 2 of these inner terms into 1 term. So right now what I'm looking at is these 2 terms right here, because if you notice, they both have a common factor of y. So if we pull this out, we can find that those 2 terms are actually equal to the product of y times the sum of z and not z. And remember that guy George Boole? Well, not only did he make Boolean algebra, but he also made a bunch of theorems for it as well. And the first theorem we're going to apply is the complement theorem. It states that not x plus x is equal to 1. And this makes sense. If you have an OR gate and you have one input is x and the other input is not x, or the opposite of x, so if x is 1, then not x is going to be 0, then at least one of the inputs in your OR gate has to be 1, therefore making the output of your OR gate 1. So if you see here, we have z plus not z. We can apply that theorem and say, okay, z plus not z must equal 1. So this entire little bit here is going to be equal to y times 1. And as we know, anything times 1 is just itself. So what we end up seeing is that this entire expression right here that we outlined is just y. So our entire second step is going to simplify to not x times not yz plus y. Now the next theorem we're going to apply is the consensus theorem. The consensus theorem states that x plus not xy is equal to x plus y. Now, where do we see an eerily similar pattern to this? Well, we see it right here. If we just swap the y and the not yz around, we get the exact same pattern. So, this means that this inner function here can simplify to just y plus z, which means our entire function simplifies to not x times the sum of y plus z. Now there are a ton of other Boolean theorems out there, so just boop, there you go, there's the rest of them. So if we look here in Minecraft, whoa, it's so much smaller, so much easier to follow. We have not x times the output of y or z, as you can see here. And guess what? It's the exact same thing. It works. It just works. And if we really wanted to get extreme about it, we can compact it even more just by doing some redstone stuff here. Yippee, we can make it super tiny. We turned that into this, and just to make sure it works. Boom. So, that's how we compact stuff. But how does this actually apply to making a real combination lock in-game? Just make a big-ass AND gate. It's so easy. Oh, you want these three things to be the inputs? Boom, just put torches on them. Connect the rest of them up to dust. Boom, big-ass AND gate. There's your output. If these are not right, then it's not going to be right. If this isn't right, then it's not going to be right. Boom, you fucking solved it. Good job.